Welcome to Statistics in Python for Finance 372. The goal in statistics, data science, and machine learning is always to learn something about the world by examining data. For any given question you want answered by data, there are dozens of statistical methodologies you can use. Fortunately, Python has ready-made libraries for all the standard methodologies. Today, we'll go through the simplest statistics using the SciPy and StatsModels libraries. To get started, we need to make sure we have installed both the SciPy and StatsModels libraries using pip install. I've already done that on this machine, so we can continue. Next, we need to import these libraries to use in this notebook. As you can see, for these libraries, I only needed a subset of them. So instead of importing all of SciPy, I just imported scipy.stats. And instead of importing all of StatsModels, I just imported statsmodels.api. And then let's read some fake data into a data frame. Okay, you can see in this fake data, we have some market returns, some returns for an investment I, and a risk-free rate. Let's say this is daily data for a year. As you can see that these returns are in percent. We have returns of 1.6 in a day, that's percent. Let's divide by 100 just so we can do compounding by multiplying them out. Okay, and you can see that after dividing by 100, the data frame looks like this. All right, the last bit of setup I'll do is to save typing going forward, I'm going to extract these columns separately as individual variables named RI, RM, and RF. And then that way going forward, instead of having to type this df.loc ... every single time, I could just say RI. With everything set up, we can get started with some basic statistics. The first thing is a simple arithmetic mean. We can do that for the entire data frame by doing df.mean, or we can do it for individual columns by doing ri.mean. Okay, so this ri, remember, is our individual column we already extracted out. So as you can see, when you print this, printing it for the whole data frame actually tells us column by column what the means are. If I just did it for the column ri, it just gives me that one number. Of course, that's the same as this number here. Standard deviations are just as easy. We can do print ri.std or print df.std, and it will tell us the standard deviations on a daily basis for each of these variables. We often want to annualize these variables. I showed you in the lecture how to do this in a formula. For arithmetic means, it's as simple as multiplying by 252. So we can do print ri.mean times 252. For standard deviations, we have to multiply instead of by 252, we have to multiply by the square root of 252. So we do that here. There's a couple ways of doing this, but that's the square root. And we get that on an annualized basis, this investment has a 37% arithmetic mean and a 30% standard deviation. Okay, next we can do a geometric mean, and this is where we rely on one of our libraries. The library we call stats, which is this scipy.stats library. So once you have SciPy loaded, to get a geometric mean, all you have to do is stats.gmean for geometric mean, and you have to tell it what you want the gmean of. So let's do 1 plus ri. So we need to add 1 to this to make it compounding, the returns compound, because otherwise it's going to try to just multiply the ri directly by each other. Of course, then you have negative numbers, and the geometric mean doesn't work. And then, of course, we subtract 1 at the end to get it back into units of returns instead of gross returns. Okay, we talked in class about how to annualize these things. The way you do that is just compounding them 252 days, subtracting 1 again at the end. Okay, so you can see here that in terms of geometric means, we have a 12, 13 basis point daily return and a 38% annualized, 39% annualized return. You may have noticed that so far, the statistics that Python is printing are pretty ugly. They give you all these decimal places. Certainly we can't estimate these things that precisely. And it's ugly to look at. It doesn't look like a percent. So how can we make this a little bit prettier? Okay, this is going to be something important for presenting your results in both homework and the final projects. The way you make results prettier is using string formatting. Okay, so the way this works in Python is you write out a string, like in parentheses here, and then you write dot format, and then you give it the numbers you want to go into the formatted string. Okay, and this string here is going to have keys in it, which are in curly braces here. And what Python does is it takes x1 and puts it into the first curly brace it finds in your formatted string, then takes x2 and puts it into your second curly brace, etc. Okay, so you can read extensive documentation about this here, but it's easiest just to see it in an example. So let's print the daily and annualized arithmetic means using a formatted string. Okay, so first I need to store those statistics into variables with names so we can access them. So let's do this. So the way this works is we first write out how we want the actual string to look like when we output it. So let's say we want it to look like this: daily arithmetic mean, and then we're going to have, let's just write XYZ for now, basis points, And then we want, let's say, annualized arithmetic mean. And then we'll have that be XYZ percent. All right, now the way we can tell Python to insert our numbers in for these XYZs is we use these curly braces here. And then inside them, we tell it how to format the numbers. So instead of printing the entire number with all the different decimal places, we can tell it we only want one decimal place. So that would be this way. So this F is for a fixed point notation where I always have one number after the decimal place, even if it's a 0. So it's going to round to the nearest tenth. All right, and we can do that again over here. All right, now that we have our formatting string with keys in it, we can do the type.format command and tell it what numbers to put in there. So we want to put in the daily arithmetic mean and the annualized arithmetic mean. All right, now to make these actually show as basis points or percents, I need to multiply them by 10,000 and 1,000 respectively. So that way they're in the units of percent and basis points. Okay, finally, I actually want to not just create this formatted string, but print it. So let me add the print command to the beginning and the end here. And now when we run this thing, you can see that the daily arithmetic mean is 14.8 basis points, annualized 37.3%. It's a lot easier to read than these long strings we had up here. Our last topic for today is linear regressions. Here we're going to study the relationships between an outcome variable and one or more independent variables. These are also called left-hand side variables and right-hand side variables. And we're going to try to estimate this relation using a linear best fit framework. Okay, so the simplest example of this we've seen a lot in finance is the CAPM regression, where we regress excess returns of an individual investment and excess returns of the market, and we get an alpha as the intercept and a beta as the slope of that line. All right, so let's do that here for practice. So it turns out that this stats models package works very well with data frames. So if we use columns from a data frame, it's going to make much prettier output. So let's put our RI minus RF and RM minus RF into our data frame as new columns. So that looks like this, where we now have an RI minus RF column and an RM minus RF column in our data frame. So the command we need to run for this regression is sm.ols. So sm is our reference to the stats models API, and OLS is the command for an ordinary least squares basic linear regression. Okay, so you can see here all of the different things in the stats models library, but we're going to just stick with the OLS. The way we call this OLS is we need to put the left-hand side here and then the right-hand side there. Our left-hand side variable, of course, is going to be the excess return of the investment I. So we can do this here. All right, and then our right-hand side variable will be the excess return on the market. So let's grab that, put that here. The way you make sure that this OLS function has an intercept in the regression is you need to tell it to add a constant. The way we do this is we go back to the SM, the stats models library, and we do add constant parentheses that. So what this does is it tells the stats model library to take whatever we give it, add a constant to it, and then now that's a new right-hand side we're going to use for the regression. All right, so that creates a model. We need to store that model here. The way this stats models package works is you use this command to create a model, and then we're going to now tell it to fit that model. So our results are going to be model.fit. All right, and then we can get a nice summary of the results by doing results.summary. So you can see here the results of this linear regression. There's a lot of stuff in here. We're not going to go through all of it. The key bits are here in the middle. You can see the coefficients and standard errors for each of the constant and the excess return on the market. Okay, so of course this is our beta and this is our alpha. You get standard errors, you get confidence intervals, you get these things called t-statistics, you get an r-squared up here. So you get a lot of cool stuff from this output. Okay, but let's say we want to access this output. For example, let's say we want to take this alpha and format it or see some more digits of it. We can do that by grabbing the daily alpha out of the results. So we can do results.params const. Results.params gives me the parameter estimates, which are these right here, the alpha and the beta. And this we want for the constant row here because this is the alpha comes out from the constant or intercept of this regression. So we can do what we did before with the arithmetic means and present the daily and annualized alphas. Once we have this variable out here, we can put that in here. Now because this is daily, we don't just multiply by 100, we also have to annualize it. So now this is annualized alpha times 100 to make it a percent. All right, now let's change the content of the string here to say alpha instead of arithmetic mean. Okay, you run this and you get 7.9% is your annualized alpha, 3.1 basis points is your daily alpha. Finally, let's show how to do a multivariate regression, where now we have not just the market excess return on the right-hand side, we have another predictor variable on the right-hand side. Okay, and let's just generate that randomly. Okay, so you can see what I've done here is added a new noise column, which is randomly distributed with a normal distribution using this numpy.random package and scaled by 100. Okay, so you can see that this noise variable is sort of the right scale. It's similar to everything else in the data frame. Okay, now to add this to our regression, we're going to do a very similar command to what we did above. But now I'm going to sort of lay it out step by step so you can see it a little easier. So let's do y as in our left-hand side variable is equal to df.loc. For our x variable, we want to make it a little bit different than before by adding this noise column in addition to rm minus rf. To do that, we can add a constant to df.loc. We want all of the rows, but only some of the columns. The columns we have to put, if we want multiple columns, we have to put that in square brackets as well. We want rm minus rf and noise. Okay, now that we have y and x, we can create our model, estimate the model, and print some results. All right, so you can see here that as before, our dependent variable is the excess return of the investment. We have, again, rm minus rf, the market return on the right-hand side, giving us a beta. But now we have a second right-hand side variable, which is just this noise. And you won't be surprised to see that since it was randomly generated, it's not super related to ri, excess return variable. With that, you have all the tools you need to compute the statistics we use throughout this course.